So in this part, we are going to discuss the random forest algorithm. We will examine the underlying principles of the algorithm and shed light on the mathematical concepts, but without delving too deeply into complex formulas. Before we start working with an entire forest, we first want to understand a single tree. This single tree is also called a decision tree. Decision trees are a rather simple construct that can be applied to many situations. For instance, this decision tree may have led you to this video. When considering whether to watch this video, the first question was likely whether you had an internet connection. If you did, you had the option to consider whether you wanted to learn something new. If the answer was yes, you might have clicked on this video. In general, I want to mention up front that random forest is suitable for both regression and classification problems. However, in this video we will focus on classification problems to keep it simple. But don't worry, once you understand random forest for classification problems, it's not difficult to apply what you have learned on regression problems. We first want to create a decision tree for a binary classification problem. We have a feature space formed by two features or measurements, namely x0 and x1. The blue and yellow points represent data points. The color indicates that these data points belong to two different classes. We now want to try to separate these two classes as cleanly as possible by looking for thresholds along x0 and x1. An initial split could be made at an x0 value of 2.75. If the condition that the values are less than or equal to 2.75 is met, they are recorded in the left node. Here only yellow data points are present after taking this threshold. We call this an pure node. All values greater than 2.75 fall into the right node, where we still have both blue and yellow data points. This is called an impure node. Now the question is, how do I deal with this impure node? Basically, I do what I just did. I look for further thresholds. This time I search along the x1 axis and set a threshold at 6.2. Again, I managed to create a pure node with only yellow data points. However, there is still an impure node with mixed classes. So I look at my data again and consider how to make another split. The final logical step is, of course, a split at x0 less than or equal to 6.2. This allows me to ultimately create two pure nodes. I now have no more impure nodes and can thus completely separate the data. This is my feature space where I can classify my data into class 0 and class 1 using a single decision tree. You might be wondering what makes this machine learning. It's just if and else statements, and you have already learned this in the lessons about Python basics. The clever part is not necessarily the decision tree itself and how it's constructed. The special thing is how an appropriate threshold is found automatically. In the example that I have given you, I have manually set these thresholds, and that's how I reach the result. But how does a machine actually find these thresholds? The two most commonly used algorithms to solve this problem in random forest are entropy and Gini impurity. These are two different approaches to finding suitable thresholds. These two algorithms then give us insights into which feature, in our case x0 and x1, and which thresholds we should start with, and which features thresholds should follow for the split thereafter. We will start by looking at Gini impurity. It is the default algorithm used in the Python package that we will use later. Gini tells us how high the probability of a misclassification of an observation is. The range of values is between 0 and 1. 0 means a good split, so it is unlikely that we have a misclassification. And 1 means the split is not good at all. We get a lot of misclassification through a split. Let's now look at the workflow for calculating Gini impurity. We will limit ourselves to the feature x0 to keep it simple. Just keep in mind that the same workflow is applied to every other feature as well, namely x1 in our case. The table here shows the x0 values, which are plotted as points in the diagram as well, along with their class membership, 0 or 1. As a side note, this is supervised learning because we know the class membership of our data. To start with the search for a suitable threshold, we sort the x0 values. Then we can calculate the means of the consecutive values. Those values will be our potential thresholds, which we now have to test one after each other to check how well each potential threshold fits. Normally, we would start with the first potential threshold, but for this example, let's just pick out 4.25 to calculate the Gini impurity for the first leaf. We test how well a threshold of 4.25 works for the correct classification of the classes. All observation points with an x0 value of less than or equal to 4.25 are now highlighted in blue in the table and would be sorted into one category. Observation points with a value greater than 4.25 are highlighted in yellow, which would be sorted into the other category. Remember that the actual classes are also recorded in our table. Let's now perform our sorting of the observation points into the categories suggested by our threshold, 4.25, while also noting they are true classes. In total, 13 observation points have an x0 of less than or equal to 4.25, and thus land in the left leaf. Of these 13 observations, 8 have the actual class 0, and 5 have the actual class 1. On the other side, 14 observations have a value greater than 4.25 and thus land in the right leaf. Of these observations, 8 have the actual class 0 and 6 have the actual class 1. The Gini impurity for this leaf can then be calculated as follows: 1 minus the probability of class 0 squared minus the probability of class 1 squared. Let's fill this formula with numbers to get the following term: 1 minus 8 over the sum of all observations in this leaf squared minus 5 over the sum of observations in this leaf squared. This gives us a Gini impurity of 0.473 for this leaf. We remember this value and repeat this step with the values from the right leaf. We get a value of 0.489. We also remember this value and use these Gini impurities of the leaves for the next step of our calculation. The final Gini impurity of the threshold to be tested is the weighted average of the Gini impurities of the leaves. So, we take the sum of the observations in a leaf, divided by the sum of all observations, and multiply it by the previously calculated Gini impurity of the leaf. We repeat this with the right leaf and add the results to get the Gini impurity for the threshold 4.25. Of course, it is not enough to calculate the Gini impurity for just one threshold. We have to repeat these steps for every threshold to be tested, and not only for the feature x0, but for all features we have observed. A decision tree should start with a threshold and feature that has the lowest Gini. Since we only looked at x0 here, the best threshold in this case would be at 2.75. With this threshold, we already achieve a pure node at the beginning. However, if x1 had a lower Gini, we would perform our first split with x1. Let's now look at entropy as another method to determine the best threshold. Entropy is a measure of disorder. An entropy of 0 means perfect order, indicating no misclassification. On the other hand, an entropy of 1 means maximum disorder and thus a mixing of classes. Let's say we are examining forests where we only distinguish between deciduous and coniferous trees. A pure deciduous or pure coniferous forest has an entropy of 0. However, if we have a forest with 100 trees consisting of 50 deciduous and 50 coniferous trees, we have an entropy of 1. To illustrate more than just the extremes of an entropy of 0 or 1, let's assume that this forest with 100 trees consists of 70 deciduous trees and 30 coniferous trees. When we plug these values into the entropy formula, we get an entropy of 0.88. Let's apply this principle and the formula to our original classification problem, which we have already used for Gini impurity. In our original dataset, we have 16 observations of class 0, the yellow class, and 11 observations of class 1, the blue class. Plugging these values into the entropy formula, our dataset initially has an entropy of 0.975. If we now make a first decision based on the threshold of, let's say, 2.75, we can also calculate how the entropy behaves in the resulting leaves. Because we have a pure node on the left side, it has an entropy of 0. In contrast, the impure node has an entropy of 0.998. This calculation is, of course, not performed for just one threshold, but for all possible thresholds. So let us add one more threshold to illustrate the different entropies under a threshold of 4.25. However, entropy alone does not tell us whether the threshold of 2.75 or 4.25 is better. For this, we use the concept of information gain, which combines the entropy of the parent node with the resulting entropies from the split. The entropies of the individual leaves serve as weights. Information gain is defined as the difference between the entropy of the parent leaf minus the probabilities in the child nodes weighted by their entropies. When we plug the numbers into the formula, we get an information gain of 0.198 for the threshold of 2.75. And an information gain of only 0.0015 for a split with a threshold of 4.25. With information gain, a higher gain indicates a better split. Unlike in this simplified example, in reality, all possible thresholds must be tested. Let's turn our somewhat abstract example into something concrete. A famous example training dataset is the iris dataset. It is about distinguishing and classifying different iris species based on flower characteristics. Let's take petal length and petal width and try to set up a decision tree using these data to clearly distinguish between the three iris species. After the third split, we can clearly distinguish the species Iris setosa from the other two species. However, to distinguish between the species versicolor and virginica, we need to make another split. Using the feature x1, or in other words petal width, we can now also clearly distinguish these two species, having only pure nodes in our decision tree. However, decision trees have a minor drawback. They tend to overfit the data. Here's an example. If we change an observation value only slightly, the species in our decision tree is no longer classified correctly. The solution? More trees. We build a random forest. For that, we need more observation features. Now, in addition to the already known features, we also have sepal length and sepal width. In the next step, we create multiple datasets from this original dataset by randomly picking observations. Observations can indeed appear multiple times in the newly generated datasets. This process of random selection of observation is called bootstrapping. In this illustration, the IDs in the generated datasets represent the entire measurements of the observation. After individual observations have been reassembled into multiple datasets, only randomly selected features are retained in each dataset. Thus, usually none of the newly generated dataset contain the full extent of the original dataset. The next step is to generate a suitable decision tree for each dataset, specializing in splitting its respective dataset as cleanly as possible. Because the dataset contains different observations and features, each tree looks somewhat different. This process is done with way more datasets and trees than those four illustrated in this example. When we receive a new observation, we can pass its information through the trees of our forest and see which class gets the most votes. While some trees may not determine the correct class, this error is usually balanced out by the voting mechanism selecting the class with the most votes. Now let's address a few more open questions. First, why is it called random forest? The first part of the name comes from the bootstrapping steps where observations are randomly reassembled and the subsequent selection of randomly chosen features. But why exactly do we need bootstrapping? Well, it ensures that the individual trees do not look identical. If all trees were identical, they would always come to the same result, negating the usefulness of the voting mechanism. Bootstrapping helps to create many different trees, allowing the model to generalize. For the same reason, we also perform feature selection. As the number of features per tree or dataset plays a role when programming the random forest, the question often arises about how many features there should be. The rule of thumb is that it should be about the square root of the total number of features. However, it is also worthwhile to try other values. By the way, bootstrapping the data and the voting mechanism of the trees is also called bagging. But how do we know if our created random forest is good enough? To answer this, we should hold back a certain portion of our data during training to test how well the model performs on unseen data. Often, 2/3 of the data are used for training and 1/3 for testing. The data used for testing are then referred to as out-of-bag data.